All right, so last time we talked about the sun and the sort of general overall structure of the sun, the parts of the sun's atmosphere and stuff, and just the basic idea of nuclear fusion. What I want to do today is expand upon that, talk about nuclear fusion in a little more detail, because when we talk about stars in general and the evolution of stars, we're going to have to understand maybe not the technical details of this process. In other words, I'm not going to be having you do calculations and stuff, although we will do some calculations in a little separate lecture that you won't be responsible for doing yourself. I just think it's really useful to show you the numbers and see how this actually works out for a star like the sun. But understanding how elements fuse together into heavier elements is going to be crucial for understanding, first of all, where all the chemical elements come from, and second of all, for understanding the evolutionary process that stars go through, especially stars more massive than our sun that go through a series of fusion steps as they go through their life. So we talked about the fact that the place where fusion happens in the star is not the whole volume of the star. No fusion is happening on the surface of the sun. No fusion is happening until you get all the way into the middle, where the temperatures and pressures are high enough to fuse hydrogen together. And we'll talk about why it requires high temperatures and pressures in a minute. So near the surface of the sun, the temperature is a few thousand degrees, the pressure is a few hundred atmospheres. But once you get to the core, the temperature is millions of degrees and the pressure is billions of atmospheres. And that's what's required to make nuclear fusion happen. So we talked about the fact, we sort of named the process as nuclear fusion. It's the fusion of hydrogens together to make helium, and that process releases energy. It's the same process that powers a hydrogen bomb. It's the conversion of a small amount of the mass of the hydrogen into light and into energy. And we talked about the fact that Einstein's formula E equals mc squared tells us that it's possible in certain cases, in certain situations, to convert what we think of as matter into energy and vice versa. So the energy from nuclear fusion comes from the mass of those hydrogen atoms. Not all of the mass, a little bit of the mass. We didn't talk about the history of our understanding of the heat of the sun. It turns out that, first of all, Einstein's paper on relativity with E equals mc squared in it wasn't published until 1905. It wasn't until in the 1920s that Eddington proposed that nuclear fusion, the fusion of hydrogen to helium and the conversion of matter into energy, was the process that powered the sun. Before that, we really didn't have any good ideas for where the sun's heat even came from. Back in the 1800s, well, I mean, I guess originally, a long time ago, people thought the sun might just be burning like a fire, right? Once we understood chemical reactions and what burning is, which is the combination of things with oxygen, there's not much oxygen in the sun, so it can't be burning, but also understanding how much energy the sun gives off. If the sun was on fire, we know how much energy a fire has. The sun would completely burn itself out in a few thousand years if the only source of energy was chemical combustion, because chemical combustion doesn't give off that much energy. So we knew that the sun can't just be on fire. What are some other options? One of the options that was considered was that the sun is heated up by little comets and asteroids constantly crashing into it and heating it up. But if you do a calculation of how much matter would have to be crashing into the sun every day, you get a ridiculously huge amount that can't possibly be true. The best idea in the 1800s was that the sun's gravity is pulling it in and it's being compressed by the pressure of gravity. And the sun just shrinks a little bit every day in order to, and that shrinking, that compressing of the gas heats it up. It's not a crazy idea. When you compress a gas, it does heat up. The sun is really, really big. So shrinking a millimeter a day or a centimeter a day, it could last for a really, really long time. We did the calculations, or actually William Thomson, Lord Kelvin did the calculation back in the 1800s. And the answer he came up with was that if that is the source of the sun's energy, it could keep doing that for a few 100,000 years, maybe a million years or so before, if it started the size of Mercury's orbit, it could keep up this process of shrinking and compressing and heating up its own gas. for hundreds of thousands of years, maybe 1,000,000 years tops. And this was, Kelvin was mid-1800s. There were other things happening in science in the mid-1800s that were relevant to this question of how old the sun is and how old the earth is. One of those things was in geology. People were trying to figure out, when we look out and we see mountains and canyons and things in the world, are those things that happened gradually through the action of wind and water erosion and rivers and stuff like that? Or are they things that happen catastrophically through volcanic eruptions and huge earthquakes? What made the Grand Canyon? Was it a giant earthquake that split the earth apart and made this huge canyon? Or was it the slow erosion of the Colorado River eroding away the rocks? We know nowadays that it's the latter, and you probably all learned that in some science class some way. But in the 1800s, nobody was quite sure. And those two classes of thought about geology were called catastrophism, where things happen rapidly, and uniformitarianism, where things happen slowly. Whether or not you believed in uniformitarianism or catastrophism was related to whether you believe the Earth is really, really old or relatively young. In order for uniformitarianism to be true, in order for erosion to have eroded mountains the size of the Rockies down to the size of the Appalachians, or to carved away the Colorado River to carve away the Grand Canyon, the world would have to be millions of years old, maybe tens, maybe hundreds of millions of years old. I'm not sure anybody was kicking around the number billions yet in the 1800s, but now we know that the Earth and solar system are billions of years old. So when Kelvin came along with his calculations that the Earth and the sun can't be any older than a few 100,000,000 years old, that was seen as evidence against uniformitarianism. The other thing happening in a different science was in biology. In the late 1800s was the time when Darwin published his theory of evolution by natural selection, by which species form through the slow accumulation of mutations and hereditary traits that are selected for because animals that are more fit to reproduce and live in a particular environment preferentially leave those adaptations onto their offspring. Well, the thing about evolution via natural selection is it has to take a really, really long time, probably millions of years or tens of millions of years or hundreds of millions of years or even billions of years. If physicists are telling us, the sun and Earth are probably only a few 100,000, maybe 1,000,000 years old tops, then that is seen as evidence against the possibility of this kind of slow, gradual evolutionary process. So there were reasons to believe from physics that the universe wasn't as old as geologists and biologists wanted it to be or needed it to be in order for their theories to be true. And that tension existed through the late 1800s. When Einstein came along in 1905 and basically told us, hey, there's a whole new way to make energy that we didn't know about before, and Eddington came along and showed that this form of energy can actually provide energy to the sun for billions of years. And we'll talk about, we'll do that calculation in a separate little lecture next week. In fact, I may actually do it tomorrow. I haven't decided if we're going to do a lab tomorrow. We'll probably do something, but I haven't decided what. Suddenly the physicists say, oh, the sun could be billions of years old and not run out of energy. So this was important at the beginning of the 20th century to confirm that these long timescales that we need for geology and biology are actually viable. Anyway, that's a little tangent, but it's an important tangent. It's important to understand that there's this feedback between different fields of science where one of them informs the other. And the age of the sun and earth was a really, really important and interesting topic in the end of the 1800s. And it's kind of remarkable to me that it's been less than 100 years that we've understood what makes the sun hot, that we've known about this process called nuclear fusion. Let me go back to my presentation now. Oh, this always screws up when I pause it. Hold on a second. Cancel. Share. Fusion. Play. Okay. So because nuclear fusion involves E equals mc squared, it involves nuclear energy, not chemical energy. It provides way more energy than any chemical process we know about. We want to talk about some of the details of the process for right now. So let's take a look at the kind of cartoon version of fusion that we looked at last time. All right, there's a little video glitch here. Hopefully everything is working okay now. So we talked about the fact that the simplest element is hydrogen. Hydrogen is just, oops. Microphone was off there for a second. I had to adjust something. We talked about the fact that the simplest element is hydrogen. Hydrogen is just a proton and an electron. The next most complex chemical element is helium. Everything in the periodic table is made of protons, neutrons, and electrons. The atomic number of an element is just how many protons it has. So hydrogen is element number 1 with 1 proton. Helium is element number 2 with 2 protons. Lithium 3, beryllium 4, boron, carbon, nitrogen, oxygen has 8, and so on. For the purposes of this discussion, we need to distinguish between the number of protons in the nucleus and the total number of particles in the nucleus. So hydrogen has 1 proton and nothing else. Most hydrogen, we'll talk about that in a second. Helium typically has 2 protons and 2 neutrons, so it has atomic number 2 for 2 protons, but atomic weight 4 for 4 particles altogether in the nucleus. Carbon has 6 protons and 6 neutrons, so atomic number 6, atomic weight 12, give or take. That's not counting the electrons. We also need to talk about isotopes. Isotope is a version of a chemical element that has a different number of neutrons than usual. For example, hydrogen is usually just a proton and nothing else in the nucleus, but you can also have hydrogen with a proton and a neutron. That is still hydrogen because it still has 1 proton, but it's a heavier version of hydrogen, or an isotope of hydrogen. The particular isotope of hydrogen with a proton and a neutron in the nucleus is called deuterium, sometimes heavy hydrogen. And it's important in astronomy, so we need to know what deuterium is. So deuterium is a heavy isotope of hydrogen that also has a neutron in the nucleus, which hydrogen usually doesn't. You could also have, for example, helium-3, which would be an isotope of helium that instead of having 2 protons, proton, proton, neutron, neutron makes 4. Instead of having 2 neutrons, just has 1 neutron, so just 1, 2, 3 particles in the nucleus. So isotopes are just different versions of chemical elements. Now, what is going on in a nucleus, and what are neutrons doing in there anyway? We know, or hopefully you know from other science classes, other places, that protons have positive charge, electrons have negative charge, and that things with opposite electrical charges attract one another, so the electron is attracted to the proton, which is what keeps it trapped in an atom. And things with opposite electrical charges, things with like electrical charges repel one another. That means that in the nucleus of an atom, 2 protons in the nucleus have a repulsive electrical force between them, which raises the question, why are they all stuck together in the nucleus if there's a repulsive force that wants to push 2 protons apart? This is probably a fact that was never mentioned in your middle school chemistry classes, let's say, when you learned about the structure of atoms, that there are protons in the nucleus, but why do those protons stay in the nucleus if there's a repulsive force pushing them apart? Shouldn't the nucleus of every atom come flying apart? Well, the nucleus of every atom wants to come flying apart. If the only force in nature was electricity, it would. But there's another force in nature besides electricity called the strong force, or the nuclear force, or sometimes the strong nuclear force. And the strong nuclear force is an attractive force that protons and neutrons feel for one another. Electrons don't feel this force at all. It's only protons and neutrons and the smaller particles inside of them that feel the strong nuclear force. A way to think about the effect of the strong nuclear force is, well, the defining characteristic of the strong nuclear force is that it is very strong, stronger than electricity, but it has a very short range. In other words, it only kicks in when two things are very close to one another. One way to imagine the strong nuclear force is to imagine you've got two magnets and you've got the two like poles of the magnets pushing each other apart. Okay, so you've got, say, the two north poles of the magnet and you're trying to get them together, but that magnetic repulsion is pushing those two magnets apart. But you put Velcro on the two magnets. So you push them together, and when you get them very close, the Velcro holds them together. The magnetic force is still pushing them apart, but the Velcro has grabbed on, and the Velcro is stronger than the magnetic repulsion. So you can think of two protons in every atomic nucleus as being like very strong magnets that want to push each other apart, but they're Velcroed together by this thing called the strong nuclear force. The Velcro doesn't do anything when they're far apart. Right? Velcro has to be very close for the two things to connect together. So you can think of the strong nuclear force as the Velcro that holds together protons if you get them close enough together. And there's the trick. And there's why nuclear fusion requires very, very high temperatures and very, very high pressures. Normally, two protons want to push each other away. They don't want to be anywhere near one another. The only way to make them stick together into something bigger is to really smash them together hard so that you're overpowering their electrical repulsion, which requires them to be moving very fast and being pushed very hard together. So the only place this happens in nature frequently is in the insides of stars, where there are these enormous pressures of billions of atmospheres, enormous temperatures of millions of degrees that can overcome the repulsion between two protons and stick them together. So they Velcro together with the strong nuclear force. You can't just have a ball of protons, though, not for very long anyway, because the electrical repulsion will overpower the nuclear Velcro and cause them to come flying apart. You need more Velcro to hold together a bunch of protons, and that's what neutrons do in the nucleus. Neutrons don't have an electrical charge, so they don't feel the electrical repulsion that the protons feel, but they do feel the strong nuclear force, so they do provide additional Velcro or glue to hold the nucleus together. So for any number of protons you might imagine, like 6, there's a acceptable number of neutrons to help glue them together. 6 works, 7 works okay, 5 works, but not for very long. So every element, 6 is carbon, 6 protons is carbon, every element has a typical number of neutrons that are doing the job of helping to hold that nucleus together. And the isotopes are just slight variations in the number of neutrons. So there's usually a most stable isotope and then a couple of isotopes that are kind of stable, but not as stable as the one with just right number of neutrons. So what happens in an actual star when we fuse hydrogens together to make helium? So here's 4 hydrogens, 4 protons, 4 electrons. Usually in the core of the sun, it would exist as a plasma where the electrons are just free to move around willy-nilly. They're not bound to a proton the way they are in a hydrogen atom here on the Earth. The process starts with combining, quote unquote, a proton and an electron to make a neutron. That's not actually what happens, right? That's the cartoon version of fusion that we talked about last time. But if we could combine a proton and an electron to make a neutron, then we've got the raw material to make a helium, right? 2 neutrons, 2 protons, 2 electrons. And we talked about the fact that when we do this, the mass of the helium actually winds up less. But there's actually a couple of intermediate steps that happen. The first thing that actually happens is we form 2 deuteriums. Deuterium is the heavy isotope of hydrogen, a proton and a neutron. And then those 2 deuteriums fuse together to make a helium. The end result is 4 hydrogens went in, 1 helium came out. But that's not exactly what happens. And I want to talk about the details of that. But just to remind ourselves one more time, that if you add up the mass of 4 hydrogen atoms and compare that to the mass of 1 helium atom, you will find that a little bit of mass gets lost in this process. And that little bit of difference in mass winds up turning into energy. It winds up in the form of energy, either light energy coming out of this process or kinetic energy, just the motion of the helium atom when the process is all said and done. And so we've converted some matter into energy. And again, we'll talk about exactly where that matter comes from at a later time. So when hydrogen is fused into helium, some of the mass of the original hydrogen atoms is converted into energy. It's interesting to ask, before we go any further into the details of the fusion process, which are a little more complicated than we've given on so far. It's interesting to ask the question, can we do this? Can we make this process happen, fusing hydrogen into helium on Earth? Because it is sort of a source of energy. The answer is absolutely 100% yes. We have made it happen before. That thing is called a hydrogen bomb. A hydrogen bomb releases a huge amount of energy, but it does so in an uncontrolled and destructive way, right? We can blow up a city with nuclear fusion and release a huge amount of energy in a very short amount of time. But that's not really the question that I was getting at. The question I was getting at is, can we make nuclear fusion happen in a way that's constructive, in a way like we burn fossil fuels to make energy and heat and electricity and don't blow up our cities? And the answer to that is maybe. We think it's possible, and we've been researching it for a very, very long time. The trick to making fusion happen on Earth is, first of all, you need temperatures of, remember, millions of degrees and pressures of billions of atmospheres in order to push these hydrogens together hard enough that they stick. Well, suppose you heated up hydrogen gas to 1,000,000 degrees. What would you keep it in? Right? You can't make a container that holds 1,000,000-degree hydrogen gas. The container would melt no matter what it was made out of. So the trick for making fusion happen on Earth is creating these 1,000,000-degree temperatures and billions of atmospheres of pressure, but containing that reaction so it doesn't cause a big explosion, in which case what you've made is a hydrogen bomb, not a hydrogen reactor. There have been experiments on Earth using, for example, really, really strong magnetic fields. This is a picture of something called a tokamak. It's sort of a magnetic donut. And inside that magnetic donut is a very strong magnetic field that confines the hydrogen gas to a little tube inside the reactor that doesn't actually touch anything. It just touches the magnetic field. So ways to confine this very, very hot plasma are hard to construct. Because you've got to contain huge amounts of energy in a small space. We've actually made nuclear fusion happen in the lab this way. We've created fusion reactors that fuse hydrogen into helium. Why don't we run our electricity off of nuclear fusion power plants then? Well, because the amount of electricity it took to make the electric fields and magnetic fields to contain the plasma is more energy than the plasma gave us when the fusion was created. So we haven't reached this break-even point where the amount of energy it takes to make the fusion happen is less than the amount of energy we get from the fusion process itself. You might say, wait, don't we have nuclear power plants already? Aren't those a thing? Nuclear power plants are a thing, but they don't use nuclear fusion. They use nuclear fission. Nuclear fission is when you take big atomic nuclei, like, for example, uranium, and you have those uranium nuclei split in half, and that releases energy. So fission is the splitting of big nuclei. Fusion is the combining of small nuclei. Nuclear fission produces a lot of energy as well, and that's what hydrogen bombs, fission bombs like uranium nuclear bombs, plutonium nuclear bombs use nuclear fission to create energy and to blow things up. And in that process of a uranium atom splitting into two smaller atoms, typically what happens is those smaller atoms are radioactive. So nuclear fission produces a lot of radioactive waste. The products of that fission process, that splitting of uranium and plutonium, are themselves radioactive stuff. And then you got to figure out what to do with all this radioactive stuff you made. That's not true for fusion, right? The process of fusion, you take two hydrogens together, you make a helium. Helium isn't radioactive. It isn't poisonous. It isn't dangerous. It's actually useful. So the waste product of nuclear fusion is much cleaner than the waste product of nuclear fission. and would be a huge improvement to have nuclear fusion plants over the nuclear fission power plants that we have today. Here's another picture of a system that actually uses lasers to confine the plasma where nuclear fusion is happening. So all these little things pointing into the center are lasers shooting a laser beam at this little region of hydrogen gas. And the light you see there is that hydrogen gas fusing into helium. It's like a tiny little star inside this laboratory vessel. And the pressure of the light pushing in from all directions keeps that plasma briefly confined. But again, we made fusion happen, but the amount of electricity it took to run the lasers was more than the amount of electricity from the little bit of fusion we've got. So we haven't reached that break-even point. The joke about nuclear fusion is if you ask physicists, how long will it be until we have a nuclear fusion power plant, a reactor, a viable nuclear fusion reactor? They will say, oh, about 30 years or so. The problem is, if you would ask them 30 years ago when we would have a viable nuclear fusion reactor, their answer would have been, oh, about 30 years or so. I've been saying that for a really, really long time since I started teaching. And then just about 6 months ago in Europe, I think in France, they're building a next generation experimental nuclear reactor. And I heard an interview with one of the directors of the scientific facility, and he was asked by the interviewer, so when do you think we'll have viable nuclear fusion power? And his answer was, oh, 25 or 30 years or so. So we keep saying that it'll be a couple, 2 or 3 decades, because the problem is a bigger technological problem, I think, than we realize. And while we're making advances, the reality of using this as a viable power source gets pushes that horizon further and further and further back. So this model that I've shown you where 4 hydrogens go in, sorry, I clicked one, I'm clicking through too fast here. Let me go back, go back. Oh, what's happening here? Hold on a second. This idea that all that happens in fusion is 4 hydrogens stick together and 1 helium comes out is really an oversimplification of the process. We want to get a clearer picture of what really happens in nuclear fusion so we can understand what happens in stars, and so we can understand a little bit more about some other observations that are really, really important in astronomy. The first oversimplification is that it's not true that a proton and an electron just go together to make a neutron. That's not really what happens. What happens typically is that 2 protons collide with one another, and one of those protons turns into a neutron plus a positron. A positron is an anti-electron. It's the antimatter partner to an electron. It's an electron with a positive charge. Now, there's nothing weird or mysterious about antimatter. It's just particles that have the opposite charge from the normal particle. So most protons are positive and electrons are negative. But there are also particles called antiprotons that are negative and particles called positrons that are positive. And just the universe doesn't have very many of those. We can make them artificially in the lab, but in nature, most protons are the regular kind of proton with a positive charge, and most electrons are the regular kind of electron with a negative charge. But antiprotons and positrons do exist. And the laws of physics allow an electron and an anti-electron to come together and just annihilate one another and turn directly into light. So what happens is 2 protons go together. They make a proton and a neutron. That's a deuterium nucleus, a heavy hydrogen nucleus, an isotope of hydrogen with a proton. And it releases a positron. And that positron will go on to collide with an electron elsewhere in the sun, and that will give off some light energy that will eventually become part of the light of the sun. This process of 2 protons going together and making a deuterium is the first step in something called the proton-proton chain. And the proton-proton chain is one of the most important processes that happens in the sun. So 2 protons come together, turn into a proton and a neutron, release a positron. That positron goes off to collide with an electron. They annihilate. That gives off some light. This deuterium that we've created, this proton and the neutron, will eventually get hit by another proton. That creates something that's almost helium, but remember, a stable helium nucleus has 2 protons and 2 neutrons. This is just 2 protons and 1 neutron. That's called helium-3. It's an unstable, too light version of helium with not enough nuclear glue to stick it together. So most of those helium-3s will just fall apart again into deuterium and a proton. But every once in a while, two of those helium-3s will collide with one another. When two helium-3s collide, they typically will form a helium-4, and the other two protons will just go free, okay? And those two protons that leave this process are now free to fuse with two more protons again. They're free to participate in further nuclear fusion. But now we've got our helium-4 nucleus, stable, 2 proton, 2 neutron helium, which is the end product of nuclear fusion. Okay. So the net effect is that, and this is a complicated drawing, but 4 protons go in and 1 helium comes out. But the actual process, 2 heliums fuse into deuterium, that releases a positron. That gets hit by another proton, that makes a helium-3. That process happens somewhere else in the sun, and those 2 heliums crash together to make a helium-4, releasing those 2 protons. So the net result is 1, 2, 3, 4, 5, 6 protons went in, 2 protons came out. So a net of 4 in and 1 helium-4 out. Notice that in 2 places in this process, energy is released. Energy is released when the deuterium and the proton combine to form a helium-3. That wiggly line with a Greek gamma next to it is a photon of light. And energy will be released when this electron, anti-electron, this positron collides with an electron. There's also a little particle hiding in here we're not going to talk about just yet. Okay, so this is the proton-proton chain. One of the other things to look at in this process are the numbers. For an individual proton in the sun, it might be 1 billion years before it finds another proton to collide with and fuse with. Once it forms a deuterium, if it doesn't get hit by another proton in the next second to form a helium-3, then that thing will probably fall apart again. Once you make a helium-3, the chance that it will collide with another helium-3 is something that happens only once every 1,000,000 years for any individual helium-3 nucleus. So the actual, if you're a proton and you live in the core of the sun, you could sit around for 1 billion years without ever finding another proton moving fast enough to hit you and fuse you into a deuterium. If you're a helium-3 in the sun, the chance is only 1 in 1,000,000 that you'll ever find another helium-3 to collide with. So that makes it seem like, well, how could there be enough fusion happening in the sun if it takes 1 billion years for any proton to find another proton? Well, there are there's a huge number of protons in the sun. So even though this process is only happening once every 1 billion years for any particular proton, there are trillions upon trillions upon trillions of protons doing this all at once. And again, we'll do a calculation showing that this is a viable process at some later point. That's not the only thing that's happening in the sun, the PP process, the proton-proton process. There are all sorts of other fusion reactions that have the net effect of fusing 4 hydrogens into 1 helium, or 4 protons into a helium-4 nucleus. I don't expect you to memorize or follow the details of this process in any kind of way that you'd be able to reproduce on an exam or whatever. But I do want to show you this process because it is important to understand that there are other things going on inside of stars than just protons colliding with other protons. This is a process called the CNO cycle, C for carbon, N for nitrogen, O for oxygen. I said the sun was mostly hydrogen and helium, and it is, but at the 1% level, there are other atoms like carbon and boron and lithium and what have you. And imagine there's a carbon atom in the sun. It's carbon-12. Carbon-12, 6 protons, 6 neutrons. That carbon-12 nucleus can get hit by a proton. If the carbon nucleus absorbs a proton, it's not carbon anymore. It's the next element up in the periodic table. The next element up in the periodic table from carbon is nitrogen. So it's nitrogen 13, right? It's got an additional particle now, so its atomic weight is 13. Nitrogen 13 is not stable. It will decay through a process called beta decay, where one of its neutrons turns into a proton. That will turn it from nitrogen 13 into carbon 13. Carbon 13 is an unstable isotope of carbon. If that carbon 13 gets hit by a proton, it can turn it into nitrogen 14 with 7 protons and 7 neutrons. That's the stable isotope of nitrogen. So that nitrogen is perfectly happy to sit around in the sun being nitrogen, and that's where the nitrogen in the sun comes from fusion with carbon. If that nitrogen 14 gets hit by a proton, though, that can fuse into the nitrogen and turn it into a different element. If we add a proton to nitrogen, it goes from atomic number 7 to atomic number 8. Atomic number 8 is oxygen. So that makes oxygen 15. Oxygen 15 is an unstable isotope of oxygen. The stable version of oxygen is oxygen 16. So this unstable oxygen nucleus wants to be something else, and it turns into something else by beta decaying one of its neutrons turning into a, well, actually, no. The easiest way for oxygen 15 to become stable, yeah, is to beta decay, to have one of its protons turn into a neutron, which takes it back down from oxygen to nitrogen, and it's lost a particle. So now what it's simply turned a proton into a neutron. So it hasn't changed its atomic weight. So that turns it into nitrogen 15, and it gives off a positron. The next step in the process, nitrogen 15 is unstable. It doesn't want to be nitrogen 15. It's not the right amount of glue to hold together a nitrogen. And it decays by a process where if it is hit by a proton, it will give off an alpha particle. I said the other day, an alpha particle is 2 protons and 2 neutrons that are stuck together. Well, an alpha particle is just a helium nucleus, right? It's helium-4, 2 protons, 2 neutrons. And when the nitrogen 15 is hit by a proton and loses those 2 other protons, it becomes carbon-12 again. So we started with carbon-12, nitrogen 13, carbon 13, nitrogen 14, oxygen 15, nitrogen 15, all the way back to carbon-12 again. So the carbon-12 can now participate in this cycle again. What has happened? If we're back to the same carbon, has anything happened? Yeah, what has happened is 4 protons went into this process and 1 helium nucleus came out. So we have fused 4 hydrogens into a helium through this complicated, convoluted nuclear reaction of carbon turning into nitrogen, turning into carbon, turning into oxygen, back again. The net effect is that 4 protons went in and 1 helium nucleus popped out. So we have fused hydrogen into helium just through a very complicated process called the CNO cycle. So there are other cycles like this that happen in the sun and other stars as well. So the process of fusion is more complicated than just you stick 4 hydrogens together and you get a helium. But the net effect is always the same. 4 hydrogens go in, 1 helium comes out. In this process of talking about fusion, I have left out an important little bit, which is a particle that you may have noticed when I showed that particle, the proton-proton change, that I didn't talk about. It is not true exactly that you can take 2 protons, stick them together, make a deuterium nucleus and a positron. There is a particle that I left out of this process. That particle is called the neutrino. A neutrino is a little, almost invisible particle that is present in some nuclear reactions. So what really happens when you turn a proton into a neutron by banging it with something like another proton is that proton turns into a neutron plus a positron, an anti-electron, plus a neutrino. And neutrinos were a particle we didn't even know about until the 1940s, 1950s. But it turns out that they are actually really, really important in astronomy. So what I'll do on Monday is I'll give a little lecture about neutrinos. This is really good timing, actually, because this is kind of a esoteric tangent to our astronomy discussion. But we are in the process next week of studying for the midterm exam, and the midterm exam stopped in the last class. So if we do a little bit of esoteric tangents for the next couple of weeks, while we're talking about material that's not going to be on the midterm, it's a good time to do that. So the timing is actually really, really good to take a step aside and talk about neutrinos. So that's what we'll do on Monday. We'll talk about neutrinos and why they're important to physicists. And the neutrino stuff won't be on the midterm exam. The stuff we did today about the proton-proton chain and the CNO cycle, that won't be on the midterm exam. All you're responsible for knowing in the midterm exam is, what is fusion? Hydrogen's fused into helium. What's the source of energy? E equals mc squared. Some of the matter turns into energy. That's all that we'll be responsible for in the midterm. Okay, so we'll go ahead and stop there. We're at a little more than 45 minutes. And we'll talk about neutrinos on Monday, and then next Tuesday we'll talk about the fusion processes that happen in more and more complicated stars. We're on the verge of being able to kind of leave our solar system and stop talking just about our sun and talk about what happens in other stars as well.